Good morning, everyone. So today we're going to continue our discussions on titanium compounds for an anti-cancer application. And then we will transition into discussions of metal complexes that have a built-in response. And so this response is broader in the sense of the different types of medical applications in which they are used for. All right, so let me go ahead and start projecting. All right, so at the end of our previous lecture, we were talking about the ability of transferrin, serum transferrin, to bind titanium and potentially deliver into the cellular environment. And so what I was emphasizing here was basically an overview of what is believed to be the process by which titanium can enter through this endocytotic process. And so the key difference between titanium versus how iron is proposed to be delivered into the cellular environment has to do with what occurs within the endosome at a pH of 5.5, where in the case of iron, iron gets reduced to iron 2+, and so that reduction event is believed to be critical for the iron to then be delivered out of the divalent metal transporter. But in the case of titanium, that is not so clear because titanium, as I mentioned in our last lecture, is really a redox inert and basically will remain as titanium-4. And so it's proposed that a chelator comes into the endosome and is able to remove titanium from transferrin. But then how that metal is actually delivered into the cellular environment is not entirely clear. But looking at titanium in terms of its importance biologically, there is really not much, I would say, credibility given towards titanium playing a role in biological processes, although there's a lot of evidence to suggest that it actually is an underappreciated metal. However, in the medical field, titanium is actually appreciated. So here I present to you a periodic table that highlights those elements that have a medicinal or some sort of application in the medical field. And so titanium is one of them. And that is because titanium is widely used in prosthetics, implants, and typically is not as a pure titanium form. It's typically in an alloy form with other metals. So the reason for the incorporation of titanium is because it displays this property known as osseointegration. Right? So basically it is a biocompatible metal that can stimulate growth. It is something, because of its biocompatible nature, it is believed to be something that would not necessarily generate allergies, although there are a few cases of allergic reactions, although it's not entirely clear if it's necessarily metal prone. Now, something that's extremely important has to do with the observation that titanium can actually leach or dissociate from the implants. And so what isn't entirely clear is whether that leaching is something that is a preliminary process, as in like it doesn't occur long term, so it's not as if there's a constant leaching of this metal. Although it is clear that when there is a collapse of the implants, that can lead to titanium entering into the bloodstream. And so the titanium that is released and is released in soluble form is captured by serum transferrin, and that interaction of serum transferrin binding that metal can lead to levels of titanium reaching as high as low micromolar in the blood. There are other indications of titanium potentially exhibiting an antibacterial effect. And so a few titanium compounds have demonstrated this property, but the mechanistic details are not entirely clear. However, titanium in the form of titanium dioxide, as I mentioned to you previously, that is the most common form of this metal in our world. Well, in nanoparticle form, and so there's actually specific sizes for this form of titanium dioxide, it plays the role of a semiconductor. And so because of that particular property, it can actually be photocatalytically activated to kill bacteria. So the underlying mechanism is believed to be that this activation can lead to the formation of reactive oxygen species. And so in that context then, if there are bacteria in the presence of the nanoparticular titanium dioxide, well, if you essentially activate it with a source of UV, that would then generate reactive oxygen species, which could then lead to an antibacterial effect. That being said, really, there has been no advancement of titanium for an antibacterial application in the clinical trials. But titanium, in terms of its anti-cancer properties, has really generated a lot of interest, and so especially this interest stemmed from the discovery of cisplatin. So, as I mentioned to you previously, the finding of this metal-based compound really revolutionized the field, and so people were very interested in exploiting other metals in terms of their broad capacity to serve as a therapeutic agent. And so when it came to looking at other metals that may have an anti-cancer effect, perhaps similar to what platinum in cisplatin is able to exhibit, people looked at these particular titanium compounds, titanosyne dichloride and butyrotitane. So initially, as I mentioned to you a few lectures ago, the search for drugs in general was really empirically based. What I mean by that is really was just looking at what type of compound might have an effect without really understanding a potential chemistry that can be exploited to have a particular application. So for instance, this compound, titanosyne dichloride, well, in a very general way, it mimics some of the features of cisplatin in that you have this cis dichloral feature that potentially is able to rapidly dissociate and enable some of the properties for titanium that platinum had. And something similar was proposed for the compound butyrotitane, and having these ethanolate groups present there that might be readily dissociated. So what was observed with these two parent compounds was that they were quite effective in terms of exhibiting a wide spectrum of effect, and they lacked cross-resistance against cell lines that had an acquired resistance towards cisplatin. And so just to emphasize that the chloride groups and the ethanolate groups, they do get rapidly dissociated from the metal center in water, and in particularly at a pH of 7.4, all the ligands that surround the titanium center actually dissociate quite rapidly. All right, so given that, one of the limitations of these compounds is that thermodynamic sink at pH 7.4, where you have a transformation of the titanium into essentially titanium dioxide in an amorphous form. And so this thermodynamic sink is actually believed to be one of the contributing factors as to why these compounds were not successful in clinical studies. So butyrotitane advanced to phase 1 trials, and titanosyne dichloride advanced to phase 2. And the reality is that the reason these compounds didn't go any further is because they simply did not exhibit much activity. They were not efficacious. As far as the toxicity, there was some exhibited, but it was really not a major concern. It was essentially that they were not active. And so to an extent, it could be this instability that was the reason for these compounds not to be active. Although, truth be told, these compounds, as formulated for administration into patients, would have already been transformed into other types of compounds. And so essentially, it's not entirely clear, the speciation of the titanium that was actually being delivered into patients. So here is a clear example of in vitro studies that did not translate into an in vivo observation. All right, so the question has been, how do these initial parent compounds exhibit any sort of anti-cancer property? So if you look closely at the literature, I did mention that these compounds were broad spectrum in terms of their effect, meaning that they were able to hit different types of cell lines. But if you really look closely at the data, you start to see some issues. So for instance, here we're looking at titanosyne dichloride tested against a few different cell lines. And here we have a family of A2780. These are human ovarian carcinoma cell lines and different variations of those. And so the variations are those that are cisplatin resistant. And so what you can notice is that there is an activity of these the titanosinate chloride against these cell lines that are cisplatin resistant. So in other words, the compound is able to have an effect where the cisplatin shows activity that is not as great. But looking really closely at these IC50 numbers compared to even those for cisplatin, even against those cisplatin resistant cell lines, you're really looking at IC50 numbers that are extremely high. Okay, and so that suggests that they're really not that effective in terms of their anti-proliferative or cytotoxic effect. But what was observed from these compounds are the following in terms of some mechanistic insight. So the compounds have the ability to arrest the cell cycle in the late S and early G2 phase. There was suggestions of titanium being able to form DNA adducts, and also an observation of apoptotic cell death being induced at any phase of the cell cycle. There was also observation of DNA strand breaks and p53 accumulation. Now, this observation of DNA strand breaks is a little bit, I would say it was a little bit confusing in terms of the origin of these strand breaks, because it wasn't clear whether the strand breaks were because of the formation of titanium DNA adducts. And so it is understood now that it's very unlikely for titanium to be able to cleave DNA, but rather the cleavage that was observed was a consequence of the apoptotic process itself. And so here's some data to illustrate some of the things that I highlighted there. So we're looking at DNA that was extracted from the A2780 cell lines. And so we're looking at the effect that is dose response, all right? So we're looking at mid-micromolar to high micromolar to now millimolar, all right? And so you see at mid-micromolar, really not much in effect on the DNA fragment. However, as you start to go into the really high micromolar, millimolar is where we start to see an effect, okay? And that effect is fragmentation of the DNA. But as I mentioned already, that fragmentation is believed to be owed to the apoptotic process itself, not because of an adduct being formed with titanium. And so to the right, we can see evidence for titanium accumulation on DNA over time. And also very importantly is the increased expression of the protein p53, which is part of the DNA repair machinery. And so we see that there is that overexpression as the concentration of titanium is increased. This is a very nice study that gives us some insight into the localization of the metal itself. So here, a technique that is called the electron spectroscopy. So essentially, we are tracking elements. And so an experiment was done with hepatocytes treated with titanosinate chloride and monitored over time. And so the main observation here is a very interesting co-localization of titanium and phosphorus signals, initially within the first 2 hours in the nuclear chromatin, and then after 24 hours in lysosomes. So it's not entirely clear what is the source of that interaction between titanium and phosphorus in both locations. However, one can speculate that that co-localization, at least within the nuclear environment, could be due to titanium adducts with DNA, and perhaps the co-localization within the lysosomes could be due to titanium interacting with phosphoproteins. So this is generally understood to be the mechanism of action of titanosinate chloride. So from the context of how titanium gets into the cellular environment, well, what we can see is that the titanosinate chloride is a very unstable compound, so that I've already established. And so what we can attribute this compound as a prodrug, where the ligands get dissociated and that titanium will bind to serum transferrin, and then it gets recognized by the transferrin receptor, and then ultimately that titanium is released into the cellular environment. It is speculated that the titanium will be coordinated by ATP, and then that ATP serves as an ionophore to deliver the titanium into the intracellular environment, and perhaps that leads to titanium going to DNA and perhaps titanium going to the lysosome. So in this process, then there is a trigger of apoptosis. So all this part is not entirely clear what happens, but those are the observations that have been made in terms of the activity of this particular compound. So it is proposed that titanium binds to the phosphate groups of DNA, which is unlike platinum, which is proposed to bind to the nitrogen 7 atom of guanine. So, and if we can attribute hard soft acid base theory here, well, that makes sense to us, right? So titanium would likely localize at a harder site, which would be at the phosphate groups, and the platinum, being softer, would localize at a more intermediate site located in the bases. And then the strand breaks, as I already mentioned previously, are maybe due to phosphate hydrolysis, but I would say highly unlikely. Now, there are others who suggest that perhaps, especially if you working with second generation titanosin compounds, that there may be an alternative mechanism in terms of the titanium effect on DNA. And that is by enhancing the stability of the CP rings, so the cyclopentadienyl rings, with the use of substituents that can help to stabilize the coordination of that metal. Then the titanium has the capacity to maintain those ligands bound to the metal, right? But then the titanium can coordinate to the phosphate group, so that you have the whole titanosin derivative moiety serving as this agent that can bind to the DNA backbone, the phosphate backbone, and distort the DNA. And so that is believed to be a possible mechanism by which the compound, to an extent, remains intact and is able to exhibit this effect. All right, and so perhaps that is a possibility for even titanosin dichloride, but then there has to be some sort of alternate mechanism by which the CP rings might be able to be transported into the cell environment and to facilitate an activity of this nature. All right, so going back to that question, right, this, how do these complexes exhibit their anti-cancer properties? And so as I already mentioned to you, there's a suggestion that serum transferrin plays a significant role. And I don't deny that that may be the case, that serum transferrin can play a role in terms of facilitating titanium cytotoxicity. I personally, so I would be in the camp to suggest that it isn't a significant role as people have previously campaigned. And so some of the observations to support titanium cytotoxicity have been the following: that titanium-bound serum transferrin can actually block the uptake of iron-bound serum transferrin. Now, for that to be a relevant property physiologically, you would really need to have a super high concentration of titanium in blood to be able to really have an effective inhibition against iron uptake. So I don't think this is entirely relevant. There are also cell viability studies that have demonstrated that the titanium serum transferrin complex really does not demonstrate a significant anti-proliferative effect. So you really have to see an effect that's really high concentration of this complex to see any sort of cell death. And so that really high concentration, well, that's to an extent, it matches up with some of the high IC50 numbers that have been reported for titanosin dichloride. All right, so here is another study where there were modifications performed with the cyclopentadienyl ring. And those modifications still didn't really produce a cytotoxic or even an antiproliferative compound that was very effective. And even then, these compounds, they were really not able to overcome interaction of that titanium with the transferrin. So nonetheless, these modifications did not necessarily improve the activity of these compounds, nor did they really overcome the ability of the compounds to interact with transferrin, which to an extent, I believe, has a sort of the opposite effect of what most people have previously proposed, and that is it actually lowers the cytotoxic property of titanium instead of actually increasing it. Right? So that's, at least in my perspective, serum transferrin is not necessarily tied into the potent activity of titanium against cells. But what about the protein serum albumin? So remember, serum albumin plays a significant role as far as metal delivery of certain essential metals. And as we saw in the case of Synsplan, it actually can play a role in terms of binding platinum and potentially perhaps enabling it to be transported into cells. And so this is actually a very interesting suggestion with regards to serum albumin because it does have a higher interaction with cancer cells than normal cells, given that it is a major source of nutrition. So cancer cells have a higher metabolic requirement, and so that lines up with that meeting that metabolic requirement. So there have been cell viability studies that have demonstrated that titanosin-bound serum albumin prepared in a ratio of 1 metal compound to 1 protein molecule really does not demonstrate much of an anti-proliferative effect. So similar to what was observed with serum transferrin, you would really need a high concentration of the titanium serum albumin compound to have any sort of effect. However, interestingly, Matthias Tact, so he has been working on a series of titanosin derivatives, one of the major ones being titanosin Y. And what he observed was that that particular compound demonstrated an anti-proliferative behavior against MCF7 cells in the presence and only in the presence of albumin. So something about that interaction enables that compound to have an anti-proliferative effect. So here I present to you sort of an overview of the different families of titanium compounds that have been made. So these are the more, the original set of compounds, titanosin chloride, butyltitane, also then second generations of titanosin. You have other researchers, for instance, Edith Shuva and Hun, who have made the selection of the salin compounds, and even have made some variation of these that are hexadentate. And so I have even worked on making a series of titanium compounds using iron chelators for a purpose that actually, in my opinion, leads to a distinct mechanism of action from some of these other compounds. All right, so here I present to you just an overview of findings in terms of the take-home message of these accomplishments made with these newer compounds. So many of these newer titanium compounds have greater solubility, are more stable to hydrolysis, and do exhibit a higher anti-proliferative cytotoxic effect. So that's something that has been observed for these different types of titanium families of compounds. In an important paper that was published by Shuva, she argues that a balance in stability and lability is critical to the anti-proliferative properties of titanium so that the metal can reach its cellular targets. And so that's something that we have already been talking about throughout the course, that you need that balance of stability and lability, because oftentimes a metal center has to reach a target. And so that compound needs to be able to have some amount of ligand dissociation in order for the metal to be able to reach the compound. And so researchers in my own laboratory have displayed that highly stable and even inert, and I'm talking about basically ligand exchange inert titanium compounds, can still demonstrate potent anti-proliferative behavior. And so the lability of these compounds can be induced by transmetallation with iron. So that's a finding that we have been exploring and trying to exploit in terms of a more, I would say, a more targeted series of titanium family of compounds. All right, so this is a really nice study that was done between two titanium researchers. So this was done by Tact and Shuva, in which they saw some really interesting differences with two different types of titanium compounds. So here you have titanium salin compound and titanosin Y. So titanosin, obviously, we already have an idea of what type of ligand that is. And so the salin compounds, so these typically are tetradentate compounds that have a phenolate component and also a amine component to allow for that potential tetradentate coordination. Right? So these are clearly two very distinct types of ligands in these titanium compounds. So what we're observing here is simply an observation of titanium uptake in cells in the presence and absence of media containing serum. All right, so why is that important? Well, serum has a number of, as I mentioned previously, proteins and other and anions that can really have an impact on speciation of metals. All right, so for titanium saline, it's observed that in the presence of serum, the amount of titanium that can enter into the cellular environment over time increases significantly, right? And the opposite is observed for titanosin Y, where it is the absence of serum that leads to a greater amount of titanium entering into the cellular environment. So clearly, the ligation of the metal center plays a significant role in terms of the potential biomolecular interactions with the media, with the biological fluids, that can have an impact in terms of how much that metal can actually enter into the cellular environment. Again, that does not necessarily mean that you're going to have a greater effect in terms of potential cytotoxic effect, as I've talked about this previously. But there is an impact in terms of the ligand surrounding the metal center and how it can affect cellular uptake. So this was a very interesting in vivo study that was performed with mice, in which so an HT29 xenograft tumor were implanted in the flank, so in the side of the mice. And so what was done was a compound. So this is a compound, I believe, that was synthesized by Hun. Right? So this is a heptacoordinate compound. So you have a coordination number of 7. So you have a saline component. So remember I was telling you about the phenyl amino features of this ligand, and then you actually have another ligand, a tridentate ligand. This is DIPIC. Okay, DIPIC is something that you have seen, although I didn't really emphasize it much when we were talking about vanadium antidiabetic properties. All right, so you have these two chelators that are bound to the metal center, and in a previous study, it was observed that this compound, that compound, I didn't mean to go that far ahead, I just want to clear up the slide, has significant anti-proliferative activity. So what they wanted to do was see how it translates into an effect, an anti-tumoral effect against these mice. And so they did a study where they use PET in order to track a radioisotope of titanium. So this is titanium-45. We're actually going to talk about this technique more closely in a later lecture, PET. But I just wanted to show the finding of this particular study, where they were tracking the titanium from this compound as it gets ingested or injected into this mouse. So we see at time points 1 minute, 10 minutes, 30 minutes, up to 7 hours. Okay, so keep in mind that the tumor in this mouse is actually in the side of the mouse. All right, so what they observed is a movement of the titanium compound through the body, and so the different arrows and different colors suggest momentary localization of the compound. And then ultimately, by 7 hours, the compound is excreted from the mouse. And what is observed is that you have basically that compound going through the whole body, but there really is not a significant uptake of that compound or localization of the compound in the tumors that were implanted in this mouse. All right, so again, this is another example of a translation that was not observed, where in vitro, this compound in direct interaction with cells has a really strong potency, but then within an in vivo model, right, you don't see as great of an effect as one would hope. Right, so limited tumor uptake of the compound. All right, so in terms of the cellular target of titanium, all right, so I already mentioned that the titanium is believed to be able to bind to DNA at the phosphate groups, okay? But there's also suggestions that titanium can hit other targets, for instance, have the ability to inhibit intracellular enzymes, either by a direct inhibition or by binding to the substrates of these enzymes and making them not recognized by the enzymes. There's also the suggestion that with the use of chelators, right, bound to the titanium center, that there can be a synergism between the titanium and the chelators to inhibit the bioavailability of the labile ion pool. And in that respect, if you if you affect that pole, right, that pole is the one that's quite reactive in terms of titanium being readily available for activity, right? Well, if you affect that pole, then the titanium does not have the capacity, the iron does not have the capacity to be trafficked for utilization, and so then you would essentially stunt cancer cells from being able to proliferate and even potentially be able to metastasize. All right, so these are proposed additional targets of titanium. And so that's where I'm going to leave you, because actually there's no true absolute understanding of what titanium does within the cellular environment. And it could be the case that depending on the ligation of the metal, you might actually have a different cellular target and a different overall mechanism of effect. All right, so as I've said to you guys previously, if you have any questions, feel free to get on your microphone, or you can type up your questions in the chat. So if you do have a question, go ahead and do that. I'm going to go ahead and transition to our next presentation. So with this presentation, we're going to broaden our perspective, and we're going to look at built-in features into metal complexes that has a response feature. And so that response can either be a triggering event to activate the metal complexes, or to release significant ligands, or even to trigger subsequent events that may have an application, a biomedical application. So I want to give you this perspective, this visual. It's very simple, where you have a metal complex and there is a key ligand, here I label that as X, and that interaction with the metal is what's going to be what we will focus on. So from one perspective is that there is a biological external stimuli, and then that's going to result in activating agent due to that metal ligand interaction. There's also the capacity of the metal compound serving as a drug carrier, such that release of X is releasing a drug. And also where that metal complex and the initial metal complex serves as a prodrug itself, then dissociation of X serves as an activation of the metal complex as a drug to induce a physiological effect, right? So we have three different perspectives of a metal compound in which a key ligand interaction can trigger these three properties. All right, so why is that the case that people want to build in a response feature? Well, as I already mentioned to you previously, the tumor environment is quite complex. And so you have a series of different cells that compose the microtumor environment. And so because of that, you do have varying environments to which you may want to build in a response to be able to trigger a certain effect. And so here I'm showing you another representation of something that I showed you previously, of this idea of the differences in the cells that constitute a tumor with respect to their proximity to a blood vessel. Okay, so blood vessel being a source, obviously, of blood, but really of oxygen. And so what is observed is that as you move away from a proximity to the blood vessel, you have a decrease in a number of features, such as a decrease in oxygen levels, decrease in nutrients and energy. And so that can also have an effect in terms of the effect, the efficaciousness of an actual drug. So a few things with regards to the oxygen level. So cancer cells consume large amounts of oxygen. The partial pressure of oxygen within a blood vessel is about 5 millimeters of mercury. This will drop to about 0, a distance of 150 to 200 microns from the blood capillary. Cells near blood vessels grow under normal aerobic conditions, but those cells that are further away grow under hypoxic, so hypoxic oxygen deprived conditions. And so those that are even further away, right, they become necrotic due to failure to perform cellular respiration. Hypoxic cells have higher levels of reducing agents like glutathione and ascorbic acid than aerobic cells. So I would say these would be the standard levels of these two reducing agents. So these are small molecule reducing agents. So glutathione, as I mentioned previously, is a tripeptide. You have ascorbic acid. So within the environment of the blood, you have these present at mid micromolar levels. But then in the cytosol, within the cellular environment, you have them at significantly higher levels. So glutathione can really reach as high as, I would even say even 11 millimolar. So that the glutathione is actually a mixture of reduced and oxidized. And similar for ascorbic acid, you also have it in millimolar concentration. So a much higher concentration than you would find in blood. So then thinking about the cellular environment, all right, let's talk a bit about pro-drug activation. So that's one of the properties that I mentioned in the initial slide. So pro-drug activation from the context of redox, okay? A common mechanism for activating a metal-containing pro-drug involves a reduction of an exchange inert complex to a lower oxidation state compound that results in ligand dissociation, all right? So here we're exploiting the property of a certain metal ion to then alter that oxidation state and enable ligand dissociation. And again, that's going to help to facilitate the activation in this context. So as an example, let's focus on platinum-4 compounds. So you guys are all experts now in platinum-2, all right? And so let's see that insight that we now have about platinum-2, how that feeds into attempts to work on platinum-4 compounds. Well, platinum-4 is low spin, 5d6, and so very low ligand substitution. The same thing is true for platinum-2 in terms of being ligand exchange inert, right? So that's not different. But what is different, and that is built into the oxoplan, this is a platinum-4 compound, which is octahedral, right? Remember, platinum-2 square planar. So a reduction event leads to the platinum center getting reduced by 2 electrons, okay? And so that reduction event now transforms the platinum to platinum-2, and so now it will be D8, and that prefers a square planar arrangement. That leads to the dissociation of the hydroxide ligands, and so now you have cisplan as your product, right? Another type of platinum-4 compound that built-in redox response is mitoplan. And so here we're actually featuring a sort of dual cytotoxic strategy where the mitoplan undergoes a reduction. That reduction leads to a release of this ligand, okay? And you have essentially the generation of what is cisplan and this other compound, and that compound has its own cytotoxic properties, being able to disrupt the mitochondrial membrane, right? So you have a built-in feature of releasing a ligand that also can synergize with the parent cisplan compound. So talking a bit about, well, proposed reductive mechanisms for these platinum-4 compounds. So this is just a general perspective of how this might happen. So here we have the structure of ascorbic acid. And so we're focusing on the oxidation state of these 2 carbons here, which are +1. All right, so if you think back to your biochemistry knowledge and being able to determine the oxidation state of carbon, and actually we reviewed this more recently, right? So just remember that information from before. All right, so we're looking at what happens to that carbon and in the context of what's happening to the platinum center. So the platinum gets reduced to platinum-2+, and so you have a 2 electron reduction, and so the electrons are coming from ascorbic acid, and so we have here that those carbons from the ascorbic acid are now +2. All right, so in terms of the mechanism by which this happens, it is believed to be an outer sphere mechanism of electron transfer. All right, so outer sphere mechanism, those who have taken inorganic chemistry will be able to better appreciate this, because what that implies is that you have an interaction that it has nothing to do with direct coordination to the metal center. Rather, what's being observed is an interaction with the ligand, okay, the external ligand, and ascorbic acid. And so the reduced agent does not coordinate onto the actual metal. And so the fundamental process that we're looking at here is what is known as a reduction elimination. Why is it a reduction elimination? Well, because you have the metal center getting reduced. Okay, that's one feature. And then you have the elimination of coordinated ligands. So that's what is built into this particular type of mechanism. All right, so what is observed is that in the presence of this, with this mechanism, DNA has the capacity to unwind in a manner that's identical to cisplatin. But what if this mechanism goes through glutathione? How can this be facilitated? So glutathione has those thiol groups that play a very significant role. So if you look at the charge of the sulfur -1, and so what happens is the platinum gets reduced, okay, and then it is the glutathione that gets oxidized. So you get the formation of this disulfide bond. And so another thing that can happen, right, so you get the release of two ligands, is, as we've mentioned previously, that the platinum 2 center can actually be coordinated by the thiol groups of glutathione forming this type of compound. And so that, as we've talked about before, that can actually have a debilitating effect on the effectiveness of the actual platinum center in terms of affecting cells. So what's observed via this type of reduction process is that the DNA effect appears to be different from cisplatin. And I think to an extent, part of the difference is how the platinum may form adducts to the DNA, where, as I mentioned previously, it might be forming more mono adducts as opposed to interstrand or intrastrand links to the DNA. All right, so continuing this discussion of prodrug activation by redox, here we're focusing on COBO3 complexes. So COBO3 complexes are octahedral, and it turns out that they can be quite suitable for the delivery of small cytotoxic compounds. But here we have a representation of this idea of this chemistry, where the COBO3 gets reduced to COBO2, and that reduction process leads to the release of that coordinated ligand X. All right, so let's talk a little bit about the metal centers. So COBO3, low spin D6, has a spin value of 0, is actually exchange inert, whereas COBO2 has a high spin D7 and it has an overall spin of 3/2, is actually exchange labile. All right, so that's actually really very interesting in terms of just that oxidation state difference can lead to a profound difference in terms of ligand exchange. But also very important is that, generally speaking, COBO2 and COBO3 seem to exhibit little to no cytotoxic or antiproliferative property. Thus, that the metal center, either oxidation state, can help to serve as effective drug carrier. All right, so here we have an example of a compound that's exploiting coordination to cobalt. This is compound SN24771, in which we have this ligand NN-bis 2-chloroethylene-diamine, abbreviated DCN, which is also known as nitrogen mustard. So here we have the COBO3 compound, which has the DCE ligand. Let me write that here, DCE. Okay, so what happens here is that there is a 1 electron reduction of the metal forming COBO2, and then that 1 electron reduction leads to dissociation of that ligand. Okay, and then there is a cyclization event of one of those arms there. Okay, so you have this aziridium ion that forms. When that forms, that particular unit is very reactive, and it has the capability of reacting to a guanine nitrogen, and what it can form is an adduct to the guanine. So here's just a visual of an adduct formation via that activated nitrogen group, right? So you have this type of adduct that can potentially form. And so you can have another cyclization event that can lead to this link to 2 guanine residues on DNA, right? So that is believed to be the proposed mechanism of that compound. So that interaction, that interstrand cross-linking can be effective at killing cancer cells. However, In vivo, this compound was found to be unstable and had low potency against hypoxic cells. All right. So another feature to discuss with respect to the microtumor environment. So in addition to a decrease in the concentration of oxygen with respect to proximity to the blood vessel is also a decrease in pH, right? And that's something that people try to exploit, a pH response, where as you are close to the blood vessels, the pH is typically 7.4. As you move away, it can reach as low as mid pH 6. All right, so here is a representation of a platinum compound that can actually be activated by pH. So here we have a platinum 2 compound where you have these bidentate ligands coordinated to the metal center. And then you have acidification of the platinum, and that leads to partial dissociation of one of the ligands. And so again, an addition equivalent of acid, HCl, leads to a partial dissociation of the other ligand. All right, so there's a downstream effect of that then leads to the platinum being able to reach a target. So the observation of this built-in pH response is the following, that when tested against an HT29 colon cell line, the IC50 value at pH 6 was actually lower than the IC50 value at pH 100. And that is because, or at least believed to be the case, that at pH 6, the platinum center was more ligand exchange prone, enabling the platinum to potentially platinate DNA, whereas at pH 7.4, that reactivity was not as present. Okay, so observed with this compound, observed increased cellular accumulation, GMP binding, DNA platination. So GMP, basically a monophosphate nucleotide with a guanosine residue, DNA platination, and greater effects on DNA secondary structure at pH 6 versus pH 7.4. Again, due to that built-in pH response. Right, you can also have pro-drug activation by enzymes. So several biomolecules that are metal dependent serve as effective drug carriers. A prime example is vitamin B12. So this particular compound is a member of the cobalamin family of compounds. It helps to maintain the normal function of the nervous system and brain, and is important in the production of red blood cells. So here I present you a structure of vitamin B12. And so a few key things to focus on. This is a 6-coordinate cobalt 3+, so that is low spin D6. That is a spin of 0. At the core, you have a tetradentate macrocyclic ligand. This is a corin, right? That essentially forms the equatorial plane of the cobalt center. Then you have what is basically is a nucleotide component, where you have a base coordination to the cobalt in the axial position here. Okay, but then you also have this other site, which is the beta ligand site, and so that can actually be modified. So in vitamin B12, that is the cyanoligand, but that is a site that can be modified and has been exploited for the purpose of prodrug activation. So for instance, there have been modifications of platinum 2, so cisplatin derivative compounds, facilitating the coordination of the platinum to the cyanoligand, right, in order to facilitate greater uptake of this compound into the body. There's also been work done with vanadium for the insulin, this word in mimicking or insulin enhancement property. Well, essentially what was done was a compound was synthesized in such a way as to have this moiety here that can coordinate to the cobalt center in the beta position. And in that way, you can get the features of the vanadium 5 group that you want in order to facilitate this insulin enhancement property. All right, so you either use directly the cyanoligand as a bridge, or you use some other ligand that can mimic the coordination of the cyano group to the cobalt center. All right, so let's look at examples of the proposed mechanism. So I'm going to go reductive activation by cellular enzymes to cobalt 2. So it's something very similar to as we discussed before, Cobalt-3 gets reduced to cobalt-2 via an enzyme, a reductase, and that leads to then the beta ligand getting released, and that beta ligand will be able to exhibit its therapeutic property, whether it's the platinum-2 type compound, whether it's the say vanadium compounds or other types of carriers. This is the proposed mechanism by which they get released. The cobalamin receptor, responsible for taking cobalamin into the cell, is relatively insensitive to the size of the groups in the beta ligand site. I would say relatively insensitive, but this may not be entirely true. So here we have an example of what I already showed you previously, where we're looking at a platinum-2 compound that has been conjugated onto the cyanoligand that's coordinated to the cobalt-3 center of the vitamin B12. All right, and so again, the idea is to deliver that platinum-2 into the cellular environment. However, in practice, the conjugates were actually less active than cisplatin itself. And here, it could have been because of the inefficiency of the receptors to transport the conjugates. So perhaps the receptors may be able to recognize and bind to the platinum derivative of the vitamin B12, but that does not necessarily mean that there's going to be greater efficiency in terms of uptake into the cellular environment. Okay. Well, now let's look at prodrug activation, but using light. And so here we're going to focus on photoactivated chemotherapy, abbreviated PACT, P-A-C-T. So compounds are activated by light to release cytotoxic agents. So light is our source of activation here. This approach is taken mainly to use for the treatment of skin cancers. However, the use of fiber optics has really allowed this technology to become more advanced, allowing treatments of cancers of bladder, lung, and esophagus. For human application and effective release of agents, it is preferable the compounds have an absorption wavelength in the 620 to 850 nanometer range. And to an extent, that is because of higher tissue penetration. But it also has to do with practical reasons, because if this is something that you have in your body that is light activated, you don't necessarily want to have something that can be UV activated if someone were to walk in, outside in presence of sunlight. Another really important feature is having a high quantum yield, and that is the ratio of the number of photons emitted versus the number of photons absorbed by the particular compound. All right, so talking about this particular technology with metals. So PACT is typically applied with organic compounds, but the field has evolved to incorporate metal complexes by taking advantage of the following electronic transitions. So here's a series of electronic transitions which several of these we're familiar with. So for instance, metal to ligand charge transfer, metal center transition. So that may seem like something you have not heard before. You actually have heard before. Those are the DD electronic transitions, because those are transitions occurring within the orbitals of the metal itself. You have intra-ligand charge transfer, ligand to metal charge transfer, ligand to ligand charge transfer, and even metal to metal charge transfer. So these types of excitations are things that can be exploited for this technology. So here is just a representation of the excitations that would facilitate these type of transitions. And so if you have not taken inorganic chemistry, you will most likely would not be able to appreciate this slide. Here we're invoking molecular orbital theory, MO theory, in terms of metal coordination compounds. And so these are molecular orbitals. And so just to highlight a little bit of what this means, here we're looking at pi molecular orbitals and the antibody molecular orbitals that correspond to the ligands. And here we have the molecular orbitals that correspond to orbitals that are metal in character, that have a pi nature. And here are molecular orbitals that have a sigma character. This is an antibody molecular orbital, but it corresponds to the d orbitals of the metal, right? So transitions within these molecular orbitals can give us the different types of transitions that can be used for PACT. All right, so I'm not going to emphasize this too much, although I will talk a bit about molecular orbital theory in a way that you guys can understand this. All right. So here is an example of photoreduction of a platinum-4 compound. So here we have this platinum-4 compound octahedral that has a ligand to metal charge transfer band at 256 nanometers. And that is because of that interaction between platinum-4 and the azides. All right. So you have that absorbance that will lead to electron density from the azides going into the metal center, right? So here, what is done is an irradiation at 366 nanometers. All right, so why 366 nanometers? So again, remember, I was saying to you previously that a favorable wavelength is something that's more in the visible range. So wavelength is chosen that is longer wavelength, right? To try to move away from the UV range to be able to facilitate this particular process of the reduction of the platinum, but also a release of the azide. So this platinum-4 compound is non-toxic to the 5637 human bladder cancer cells in the dark. Right, so the compound has no cytotoxicity in the dark. However, upon radiation, there is cytotoxic behavior even against cisplatin-resistant cells. Cisplatin-resistant version of these 537 cells. What has been observed is after radiation, there are guanine intrastrand crosslinks, okay, that actually are generated much faster than cisplatin, and the azido radical, this radical that formed, likely yields reactive nitrogen species and can generate oxidative stress. So you have the built-in feature of the platinum component, but also that azido radical that can also have its effect. Okay, so let's look at an example of the photorelease of a bound drug. So here we're focusing on 4-aminopyridine, abbreviated as AP, which is used for the treatment of symptoms of multiple sclerosis, a disease of the central nervous system. All right, so this particular molecule has a capacity of blocking potassium channels, and it can stimulate action potential and also neurotransmitter release. All right, but let's look at it from the perspective of its coordination to a metal center and how it can be how its release can be facilitated. So we're looking at this ruthenium-2 compound. Ruthenium is low spin D6. It is a coordination number of 6. You have these 2 Bippy rings, okay? And then you have the AP ligands, and there are 2 of them. Okay. All right, so what's important here? Actually, let me clean that up so you guys can see what I have written there. Well, what's important here is that there is a metal to ligand charge transfer between 400 and 500 nanometers. And that is a charge transfer between the metal and the Bippy rings, the Bippy ligands. All right, so I'm going to take a little deviation just to provide a little clarity. So let's focus on, and again, this may not be entirely understandable for those who have not taken inorganic, but I will try to bring the clarity that you need. So this is a molecular orbital representation of ruthenium as coordinated in this type of environment. So coordination number 6, all right, where we have these molecular orbitals that are labeled as the T2G, EG star, and T2G star, right? So these are different molecular orbitals. This one is a bonding molecular orbital. These 2 are antibonding molecular orbitals, all right? So there are additional molecular orbitals that are not depicted here. I'm just focusing on those molecular orbitals in which electrons from the metal can enter. So these would be the 6 electrons from the d orbital of the ruthenium-2, and they will be found in the T2G. So this would be your low spin representation of the D6. So these orbitals are metal in character, and then this antibonding orbital is ligand in character, right? So that's going to be important. So here, if we're focusing on this arrangement of electrons in the T2G orbitals, these will be the metal character orbitals, then you will have the low spin, a spin of 0. That leads to a multiplicity of 1, which is a singlet state, right? So multiplicity equals to 2s plus 1. and that equals to a value of 1. That's a singlet state. Well, if you have an excitation of one of those electrons from T to G into the T to G star orbitals, the antibonding orbitals, so let's imagine this excitation here, where you have an electron now present in T to G spin down. If you were to calculate the spin and the multiplicity, you get a value multiplicity of 1. And so this would be a metal ligand charge transfer, because you're going from a metal orbital to a ligand molecular orbital. So that transition is a metal to ligand transition. And so in terms of the multiplicity, it's 1. So what we refer to this as 1 MLCT, right? 1 referring to the singlet state. Okay. But then you can have what is known as an intersystem crossing. And that is going to be an energy that's going to flip this electron that's at the higher energy electronic orbital, so that now it is paired up. And so as a consequence of paired up, now you have two unpaired electrons that are pointing in the same direction. And so this would be now a change in your spin. This would be a spin equal to 1. Okay? And so now we will have a different multiplicity. We will have a multiplicity of 3. Okay? Still, we have a metal to ligand charge transfer, but now your multiplicity is 3. So you have a what is known as a triplet state. And this triplet state is actually longer lived. All right? So this is an important feature that we're going to look at. All right. So let's go back to the compound, the ruthenium compound with the BIP and the AP ligands. So there is a metal ligand charge transfer at 400 and 500 nanometers. You irradiate at 500 nanometers. Again, you want to get further, I guess, a longer wavelength, so further in the visible range. That then leads to an oxidation of the metal. Remember, we're irradiating at where there is a metal to ligand charge transfer. So electron density is moving from the metal into the ligand. As a consequence, then, you have a release of the two AP ligands. And so then your metal can be reduced back to ruthenium-2, because it's serving as a delivery. It's releasing that drug. All right. But what about another example, the photorelease of cell signaling molecules? So in this context, metal complexes can be quite effective in binding and transporting cell signaling molecules. As an example is carbon monoxide, right? So you guys should be familiar with carbon dioxide, perhaps more for its toxic properties. So high carbon monoxide levels, so we're talking about levels that are greater than 300 ppm, well, they shut down cellular respiration. In the United States, accidental carbon monoxide poisoning accounts for hundreds of deaths because it is colorless, odorless, tasteless, and non-irritating. This gas is also used to euthanize mice. Okay, well, at lower concentrations, so lower than 200 ppm, carbon monoxide actually has some really important properties. It is the product of heme degradation that serves as a signaling agent, has anti-inflammatory effects, promotes vascular smooth muscle tone, facilitates grafting in organ transplants, and protects against ischemia. Okay, so it protects against swelling. So as far as using carbon monoxide for a biomedical application, when we're thinking about administration, what typically is mixed with air. When it's mixed with air, it's very hard to administer in a very calculated, controlled manner. People have tried to use metal carbonyl complexes to use the metal to release the carbonyl, but even then, the controlled delivery is not as good. All right. But let's look at an example of a more controlled metal complex that serves as a prodrug, this photo CO releasing molecule, CORM, CORM. This has a capacity of release in a dose and site-specific manner. All right, so let's look at this compound. And so it's this compound here, Re, oxidation state of 1, which is a D6 electron configuration. All right, so look at the features of the compound. So we already talked about the metal. We have a BIPI ring. Okay. We have this phosphine group. We have these alcohols coordinated to it. And then you have the 3 carbonyl ligands. It turns out that this compound has a metal to ligand charge transfer at 345 nanometers. And that is because of the interaction between the metal and the BIPI ligand. All right. So if you are to irradiate at 405 nanometers, what happens is you then get release of a carbonyl ligand. And so in that way, then, using irradiation, you can have a more controlled release of carbonyl. So the compound is found to distribute to the cytoplasm and not the nuclei of human prostate carcinoma PPC1 cells. So here's just the example of what I just mentioned in terms of where it's localizing. So here are the use of dyes to be able to indicate what's observed. So here to the left, what we're looking at, let's see, A is this image. So we're looking at the PPC1 cells treated with 50 micromolar of this complex. So to the right, we have a wavelength of emission of 465 to 495 nanometers, which was collected with minimal photolysis from the 405 nanometer excitation. So it indicates the incorporation of the compound into the cytosol. So we see the compound, this blue light that's associated with that compound in the cytosol. But then, after longer-term irradiation at 4 or 5 nanometers, we see this emission in green. So there's an emission at greater than 660 nanometers. And so that suggests a transformation of the compound from the original parent compound to a compound of this nature, of the monoequated form, which has a release of the carbonyl. So what that suggests is that after 15 minutes, you start to then release the carbonyl in this controlled manner. And so we see this in terms of the change of the fluorescent property of the compound in the cytosol environment from blue to this green feature. All right. And the last thing that I want to present to you guys as far as a built-in response, because you guys will in the future have a chance to talk about this idea of a built-in response in compounds, is photodynamic therapy, or PDT, which at present largely focuses on the use of oxygen, especially within the cellular environment. So this is light-activated sensitizer to convert the triplet form of oxygen into the singlet form of oxygen, which can kill cancer cells. Right. So the first sensitizer was photofrin. Okay, so here we have a depiction of this photofrin, which is essentially an oligomer of protoporphyrin 9, right? So that protoporphyrin 9 is something that we see as part of the heme group. You can see in hemoglobin and other heme-containing proteins. So this particular sensitizer was used for surface tumors. The thing is that it has long-term phototoxicity. So this is what I was mentioning before. With some type of these compounds that are very sensitive to light, they can become they can become toxic if you expose yourself to sunlight. So here's an example of an agent that has therapeutic properties, but you have to then restrict yourself in terms of the being in the presence of light. And here, it's actually a significant amount of time. All right, so let's look at the context of these sensitizers, but introducing metals. So metals binding to organic sensitizers can enhance the photodynamic therapy effect by allowing for faster and longer-lived sensitization. So here we have a few representations here of metals that are coordinated to these organic sensitizers, right? And so it gives us a perspective of these type of compounds. All right, so here, this is probably one of you guys' favorite slides. You see it in physical chemistry, the Jablonski diagram. It looks a little scary, but it's actually not scary at all. So let's look a bit about what we see here and how it relates to the properties of these compounds and their interaction with oxygen. All right, so to the left, we have the photosynthesizer. So initially that photosynthesizer will be in its ground state and it will be in a singlet state. There will be an excitation to excited states, okay, that are also potentially singlet states. And then you have relaxations that can occur within these vibrational states to then lead to the release of a photon that generates a fluorescent signal. Okay, so that's something that can happen where you have an excitation of an electron from the photosensitizer to higher excited states, and then you have a relaxation due to an emission that gives you a fluorescent signal. All right, sorry, I'm going to clean this up a little bit. But another thing that can happen is instead of that fluorescence occurring, is that intersystem conversion, right? And that intersystem conversion being from a singlet state to a triplet state. Okay, so now you're in another excited state, but of a different multiplicity. And from there, you can have what is known as a relaxation or emission that from the triplet state back down to the singlet ground state, which is known as phosphorescence. Or another thing that can occur is that this electron in this triplet state can undergo what is known as an electron transfer. And what I mean by that is that it can interact with oxygen within the cellular environment, leading to the production of a greater production of reactive oxygen species. But another thing that can occur is that energy from the triplet state going down to the ground state, well, that can interact with oxygen itself, okay? And then that interaction can lead to a transformation of the oxygen. Well, oxygen, let me clean this up for clarity, oxygen is in a triplet state. So by interaction with the photosensitizer, you can convert that oxygen from the triplet state into the singlet state oxygen. And then that singlet state oxygen, that is a very reactive form of oxygen, and that can lead to energy transfer and also a source of cell death. Okay, remember, we're putting this perspective of these compounds taking advantage of oxygen and exploiting them to be able to induce a cell death property. All right, so let's focus on the photosensitizer. All right, so if we're looking at this from the perspective of a metal center, let's go back to our example of ruthenium. And I already talked to you about this idea of ruthenium being able to D6 going from a ground state to an excited state. So we're going here from a metal orbital to a ligand orbital, okay? And that leads to this excited singlet state, okay? But then you have an intersystem crossing that now gives us an excited triplet state. So that can represent the part of the Jablonski diagram that we see here. Excitation to excited state, and then intersystem crossing into the triplet state. Okay, so that is reflected with this example of the ruthenium compound. All right, here I give you a perspective of this idea of contrasting metal compound photosensitizers versus organic compounds versus what are known as metal organic compounds. All right, so organic compounds, those were originally the first line compounds that were used for this type of application. Well, the conversion, right, the intersystem crossing and even the relaxation is slow and slow. So that is a limitation there. Whereas the metal complexes, so a traditional metal coordination compound, you have a fast intersystem conversion, but also a fast relaxation. And that's actually not optimal either. But those photosynthesizers, the organic ones, as I showed you those examples of the protoporphyrin-like ones, we have a metal center, those actually have a nice balance between a fast intersystem crossing, but a very slow intersystem crossing or relaxation from the excited triplet state back down to the ground state. So that is actually the ideal, what people want to see. So here, instead of crossing into a triplet state from the metal, you're actually crossing into a triplet state from a ligand itself. That's what is known as an intraligand state. All right, so that gives us a perspective of a photosynthesizer. So now let's focus on the oxygen. All right, so now we should cross into something that everyone can understand. That is molecular orbital as it corresponds to oxygen. So I think everyone at this point, you guys have seen this since general chemistry, so you should be able to give me this with no problem. The molecular orbital diagram for oxygen, for the compound O2, right? So we have our oxygen on both sides, right? So we have these two atoms forming this compound. We have, focusing on the valence orbital and only the valence orbital electrons, the 2s, the 2p's, right? And then remember, we're looking at this from perspective energy, the 2s lower than the 2p's. So then you get your corresponding molecular orbital diagram. So here you get your sigma and sigma star molecular orbitals that are formed from the 2s orbitals. And then you get your corresponding sigma orbitals that form from the p orbitals interacting, and you get your pi orbitals, your pi star, and your sigma star. All right, so I'm not going to go into this in too much detail because it is something that at this point I think you guys should be able to understand, and if you haven't seen it in some time, be able to review and quickly understand. All right, but where I'm going to draw your eyes to is this part of the molecular orbital diagram, because that part of the molecular orbital diagram shows us that oxygen, this molecule, is actually a radical because it's unpaired electrons. Okay, unpaired electrons. And so when we account only for those molecular orbitals, right, our spin is 1 because we have 2 unpaired electrons. Therefore, our multiplicity is 3. So the ground state of oxygen is a triplet state. Then excited state is, imagine one of these getting flipped, okay? And so now you have 1 electron up and 1 electron down. Now our spin will be 0, and our corresponding multiplicity will be 1. So we'll now have a singlet state versus a triplet state. So the singlet state is the excited state of oxygen. So this is triplet O2. This is singlet O2. Okay, that's actually really important. So people try to take advantage of this property of oxygen, of this formation of excited oxygen to have an anti-cancer effect. So just an example, so this is a researcher, Sherry McFarland. She's at the University of Texas in Arlington. She actually came 2 years ago to give a lecture for Metals of Medicine, also for the Rice and Mark program, where she talked about her own development of a PDT application using a metal compound. And so here is an example of a clinical trial of this being performed with fiber optics, right, treating a patient. So this is an outpatient procedure. This is Theralase. This is the what she invented. Okay, so the feasibility of photodynamic therapy. Advantage: you can have targeted areas, especially with the use of fiber optics. But a major disadvantage: limited penetration if you don't have access to fiber optics. But also, very importantly, remember the complex super environment, the low availability of oxygen. If you don't have enough, you're simply not going to have much activity. Therefore, people are trying to develop this technology using other cellular species to be able to facilitate this type of effect. All right, so with that in mind, then, we conclude this discussion. All right, and so next week, we're going to have 2 seminars. So get ready. I'll be giving you guys your next assignment that's going to be based on the selection of articles that your classmates have made. All right, everyone, have a great week, and I look forward to reading your annotated bibliographies. Take care.
Profesor, ¿puedo dejarle saber algo al final de la clase?
Ajá.